This section is on continuity and piecewise defined functions, amongst a couple other things. An informal definition of continuity for a function is one where you can draw it and you never have to lift your pencil up. However, a more exact definition involving calculus is one that you should know. First of all, to be continuous at the point x equals c, f of c must exist. So this is a violation of that particular part of the continuity definition. The limit exists as we approach from each side. The limit will exist, but the point does not. This is a whole. It's also a removable discontinuity. Also, the limit as x approaches c of f of x must exist. Notice that f of c exists. There is a point there, but the limit does not. Coming from the right, you get one thing. Coming from the left, you get another. And so it's not continuous. This is also a discontinuity. And this would be a step discontinuity. It's non-removable. You cannot just plug something in and remove it. And finally, you have to combine these two and say that not only does f of c must exist and the limit must exist, but they have to equal each other. Because in this case, the limit exists and the point exists, but they're not the same. And so this is another removable discontinuity. As far as other types of discontinuities, you have your removable, which are the wholes. Non-removable would be steps, for instance, asymptotes, vertical asymptotes that is, and also oscillations. An example of an oscillation could be something where as you come to a point, it just starts to, it doesn't settle in anywhere in particular. So for instance, if you were doing the limit as x approached 0 of sine of 1 over x, this would be discontinuous by oscillation at x equals 0. Now, as far as one-sided limits goes, here we have some examples of some one-sided limits. If you take the limit as x approaches 5 from above of rad x minus 5, you get 0. Something a little more than 5 minus 5 is a little more than 0. Square root of that is 0. However, coming from the left side, as x approaches 5 from below, you're taking a square root of something very small but negative. And square roots of negatives are undefined. And the graph would look like this. And you can see coming from the right, we go to 0. Coming from the left, there's no points there. Now, this is a little bit more general. We have the absolute value of x minus c over x minus c. If you take the limit as x approaches c from the right, you will have a little more than c minus c on top, which will be positive. And on the bottom, you'll have the same thing in positive. So those cancel, you get 1. However, if you come from the left side, the denominator is a little less than c minus c, which is negative, and the numerator is the same value, but positive because of the absolute value. And so when they cancel, you get negative 1. And so graphically, if c was over here, you'd have negative 1 to the left and then an open circle, and then positive 1 to the right and an open circle. And so the limit does not exist as x approaches c as such because the limits don't equal the same thing from both sides. And we see that if we say let c equal 0, then you get this sort of classic limit as x approaches 0, absolute value of x over x, which is undefined because from the right it's 1 and from the left it's negative 1. This is called the intermediate value theorem, or IVT, intermediate value theorem. It relates to continuity and something you've generally been taking for granted because many of the functions you've dealt with in the past have been continuous, like polynomials. But the idea is if you have a continuous function and we have points at a comma f of a and b comma f of b, then for any y value between f of a and f of b, there's at least one x value between a and b, that is, c between a and b that will correspond to that y value. And one way we've taken it for granted is doing synthetic division and trying to find zeros. So in synthetic division, if you plugged in 2 and you got negative 5, that's sort of a point down here. If you plug in 1, you got 2 out, that's a point up there. And you assume then that there was a 0 of your function between 1 and 2 because you figured it had to cross the x-axis. Well, that assumption is made because polynomials are continuous and you do synthetic division with polynomials. Now, piecewise defined functions. So this is an example of a piecewise defined function. It's defined in pieces. So f of x equals sine x as long as x is less than 0, and it's x squared if x is greater than or equal to 0. Now, they don't necessarily have to be continuous. You can certainly have a piecewise defined function where you have one piece over here and then another piece which does something like this, and that's not continuous. This particular one would be because as x approaches 0 from the left, sine is 0, 0. As x approaches 0 from the right, 0 squared is 0, so they match up. So this would be a continuous function. Even though it's x less than 0, you still imagine putting 0 in there because you're approaching it as a limit. Now, for this particular one, the idea here is you want to find a value of a to make this function continuous. And so The way you do it, if you want it to be continuous, then at this point where they come together at x equals 2, you have to get them to match up. So if you plug in 2 for x, you'll have 2a plus 2. You plug in 2 for x here, you'll have 2 squared minus 1. And therefore, 2a plus 2 must equal 2 squared minus 1. So 2a plus 2 is equal to 3. And finally, a is a half. Now, as we can see in these figures below, and this is how you can put in a piecewise defined function in your TI calculator. If I choose 1 for a, so notice there's nothing in front of the x, these don't match up. I've got a line, piece of a parabola, they don't match up. Whereas if I put in 0.5, then they do connect and it's continuous. As far as the syntax here, the way to get the less than and greater than or equal to signs and all those is to press on second test, and then you get a menu of those. And what's happening is this is basically Boolean logic. If this is true, it will return a 1. It'll do 1 times this, and it'll plot it plus. If it's not true, it'll return a 0, and it'll cancel this piece out. So you only get one piece at a time.